Hello, we are Wing Design Group 8. In the following video we are going to walk you through the processes and techniques we use to design and create a wing out of foam board.
The conceptual stage helped us increase our productivity by focusing testing on designs with the highest chance of success. Our wing is composed of a main load carrying spar with ribs, a leading edge and a rear spar connecting to both an outboard aileron and inboard flap. Our initial concepts for the main spar were based on theory, allowing us to predict what designs were most likely to meet the requirements given. We determined through various statics equations that we needed a high moment of inertia and polar moment of area to lessen vertical deflection from stress and angular deflection from torsion respectively, both while weighing as little as possible. We contemplated many designs and discovered through research that I-beams, though massively effective against bending, have little resistance to torsional loading, so would need to be modified. This is unlike hollow rectangular beams which, although generally have greater mass, have a higher polar moment of area for similar dimensions. Eventually we began testing on the most promising designs. As our medium was foam board, we realized early on that bending the sheets as opposed to using adhesive increased the strength of these possible weak points whilst also being faster and easier to implement.
The spreadsheet is a useful tool for nailing down the preliminary design. The first part is about general design input. Basic parameters can contribute to calculations such as bending moments. Is structural analysis, which is the reference of obtaining the spar's cross-section. Based on requirements such as tip deflection, we can make the spar to be as light as possible while making sure it passes all the tests. The final part is to determine the geometry of the spar connecting with the ribs. By adjusting the coordinates, it provides an approximate shape of the ribs to be further designed.
CAD modeling allows us to create the different components of the wing virtually, to visualize dimensions and joining methods between parts. Parts can also be tested virtually to see what changes may need to be made. From the simulation of the wing assembly that I modeled, it can be seen that the majority of the forces and stresses act on the main spar, which are green and red, and the other components are less stressed as they are shown in blue, and so most of the design attention needs to be paid to the spar. From the simulation of a basic spar with a load on the tip, it can be seen that the majority of stresses is near to one end and the tops and bottoms, where the color is shown as red and green. The middle and other ends are blue, showing there is less stresses in this area. This helps to maximize the strength-to-weight ratio, as material can be removed from the areas in blue and material can be added more efficiently in the higher stress areas. From the simulation, I was able to design more efficient spars, reducing the material used, which saves weight, but still retains material in areas with higher stresses.
Our first attempt in the lab was a basic rectangle made from a simple sketch. However, it did not pass any stress or torsion requirements. This made our group quickly realize that a good spar design required a lot of preparation and testing before being manufactured. Going from our first design to our second and third was a big change, as we would take into account the requirements of spar geometry as well as bending and torsion tests that we would conduct in the lab. Making these changes, however, increased the weight of the spar, so in order to compensate for this, our group finalized our design by using laser cutting to skeletonize the spar in areas that were not experiencing stress. The practical work in the lab session were the catalyst to the completion of our spar design, but in order to create our perfected spar, we went through many failed attempts and iterations. These iterations were important in optimizing our wing spar in order to meet all design requirements.
In conclusion, after starting with a preliminary design for a wing spar, we settled on a final design after testing, whereby we maximized the amount of material where the highest shear force would be located. The optimization of our wing spar would not have been possible without our Excel analysis, and neither the design of our ribs without SolidWorks. Some amendments to our testing and design would be to increase the speed by which we tested the wing spar in order to save time, and to increase the strength of our ribs by making them thicker or reducing cross-sectional area of the wing spar cutout in the ribs. Thank you very much for watching our video.